What I have over here is a very interesting combinatorial problem. In fact, it can make for a very good math competition problem. In fact, the idea of it is very popular in math competition. Basically, it looks kind of long and it looks kind of complicated. However, the idea and the technique we use to solve it is super powerful, and it's widely applicable to many other combinatorial problems. So let's get right into it. Firstly, we have a regular pentagon A, B, C, D, E, and a bug starts at vertex A. Now, on each move, the bug may move to an adjacent vertex via a connecting edge. So on your first move, you can move to B or E. Of course, the bug's first move. So now that you get the idea of it, let's go over what the problem wants us to solve for. We want the probability that in exactly 10 moves, the bug will be back at vertex A, and the bug was not on vertex A at any point before the 10th move, except at the start, because at the start, you're going to be on vertex A. But for any move that is before the 10th move, you should not be visiting vertex A at all. So how can we solve this problem? Well, we might start by considering some special paths of length 10 and see where we go from there. However, admittedly, 10 is a pretty big number for a problem like this. I mean, paths of length 10, there can be a lot of them. So I think it's best to start off with some small examples. So I'm going to actually define a new variable. Firstly, I'm going to let Pn, okay, Pn be the probability that the bug will satisfy these two requirements in n moves. Okay, so just imagine replacing this 10 with n, okay? So now Pn is the probability that we're looking for. So this would mean that we are just looking for what P10 is. Okay, so as I said, 10 might be a big number for this. So maybe try something simple like P1. So what is P1? Well, first of all, in one move, you will not be back at A, right? On your first move, you're going to be at B or E. You're not going to satisfy this condition. So clearly, P1 is 0. Okay, P1 is 0. Now, what about something like P2? P2, what is this equal to? Well, observe that, again, on your first move, you're going to end up at B or E. But on your next move, your second move, you have to go back at A, right, to satisfy both of these conditions. So your last move, you have to choose only one of the paths out of the two possible ones. So it's 1/2. P2 is 1/2. Okay, great. Well, what about P3? Well, P3, we can count this, and you'll see that it's actually 0, because in this case, 3 is odd. And when you have an odd number like this, and, for example, 3, you cannot balance the moves so that you go back to A. In 2, you move away from A, but then you have to balance it back to go back to A. 3 is odd, so you can't make that balance. Now, be careful about certain assumptions. This does not mean that P odd is 0 in general. This is wrong, actually, because, for instance, P5 is actually not 0. There's actually a path of length 5 that satisfies the condition, right? So P5 is not 0. So be careful of this. It's just that 3 is smaller than 5 in this case, so you can't make that balance, and you cannot, make it back to A at the same time. Okay, so let's move on to P4. So P4. What is P4 equal to? Well, again, you must be at B or E on your, first move. And then because it's 4, you want to move away from B or E. So first of all, I'm just going to choose B because they're both symmetrical, so it doesn't matter. So if we move to B, then we must move to C. Well, what's the chance of that happening? It's 1/2. So first off, there's a 1/2. And we're not done yet, so times something. Now, when we go to C, observe that because this is 4, we have to use our last 2 moves to rush back to A. Right, we've already exhausted 2 moves. We have to use the last 2 to rush back to A. So that would be 1/2 and then times 1/2. So P4, we can deduce, is 1 over 8. Okay, well, what about, I don't know, P5? Just, continue on. P5, well, P5 is actually, getting a little bit too big at this point. We could, of course, still try brute force counting. However, when we start seeing numbers that make it even slightly more tedious, it might be a good idea to look for a general formula, some sort of elegant solution. Okay, so let's move away from P5 and let's go on to Pn for general n. Firstly, I'm going to actually derive a formula for Pn in terms of n for when n is greater or equal to 3. And the reason for this restriction is because we know that on the first move, we're going to be at B or E. But then on our second move, we have to move away from A, right? So we move to C or D. That would not be true if n was equal to 2. If n was equal to 2, we would have to move directly back to A. So this restriction is here to maintain the consistency. Okay, so now that's out of the way, let's go into the derivation. Firstly, when we were at B or E, what's the probability of us even going to C or D? It's 1/2, right? There are 2 possible moves and only one of them works, so that would be 1/2. There's a 1/2 chance to consider to begin. Now, obviously times something because we're not done. So now that we're at C or D, notice that we are basically stuck within a certain region. Because we cannot travel back to A until our last move, we are basically stuck within the region from B to C to D to E. We are basically, contained within this, you can call it an open trapezoidal region from B to C to D to E. We can only travel within, these 3 line segments. Of course, there is an A up here, right? Okay, so now we're at C or D. I'm just going to choose C because, once again, it's symmetrical. Observe that on our second last move, right? On our second last move, we have to be arriving at E or B. And the reason is pretty obvious, because on our last move, we have to use that last move to move back to A. So on our second last move, we have to be at B or E. Well, I'm going to define a new variable. I'm going to let Qn be the probability that in n moves, we are at B or E, starting from C or D, okay? So Qn is when we start at C or D, and it's the probability that we end up at B or E in n moves. Now let's calculate Qn in terms of something like Qn minus 1 or Qn minus 2, right? If we can write it in terms of like Qn minus 1, Qn minus 2, maybe even, lower indexes or indices, that could be very useful. We will get ourselves a recursive formula. Okay, so we have a new definition, but just for a moment, let us go back to here. Notice that by the time we are at C, what's the probability that we move back to B or E on our second last step? It's Qn. We literally defined it like that. However, be careful. Notice that when we move to C, or of course D, when we move to there, we already used 2 moves. So we have n minus 2 moves left. Now, by the time we have, completed our second last move, we will have moved n minus 3 times, right? So over here, when we move to C, we want the probability that we move back to B or E. But that's in n minus 3 moves in this case, okay, for in this case. So we have to multiply by Qn minus 3. I'm actually going to write that a little bit better. Okay, so I fixed it. So this is our probability, right? No, because when we're back at B or E, there's a 1/2 chance of us even moving back to A. So we have to multiply this by another 1/2. So this 2 on the bottom gets turned into 1 over 4. And we have finally derived a recursive formula for Pn in terms of Qn, or Qn minus 3. The only stumbling block is, well, what's Qn in terms of, I don't know, Qn minus 1 or Qn minus 2? That could be very useful. Okay, so let's try to derive that. Let's consider cases for where we could move starting at C. Notice that when we start at C, we could move back to B, right? What's the chance of that happening? It's 1/2. So there's a 1/2 chance. And when we go to B, what's the probability that we go back to C? We can't move back to A because that's only for the last move. So what's the probability that we move back to C? It's 1/2 again. So we multiply by another 1/2. And what's the probability that we go back to B or E on our second last move? It's literally just Qn, right? But this time we have used 2 moves. So that would be Qn minus 2. All right, looking good. Now we just need to consider the other case. What if on our first move, starting at C, we move to D? There's a 1/2 chance. So we add 1/2. Over here, the probability that we move back to B or E, starting at D, is also Qn, but we've already used 1 move, so that's Qn minus 1. And there we have it. We have a recursive formula for Qn. Now, what's so cool about this recursive formula is that we actually know what Q0 is. It's 0, because if you don't move at all, you're not going to be at B or E. Now, what about Q1? Well, Q1, that's going to be 1/2, because if you start at C over here, then the only way you're going to be at B or E in 1 move is to move to B, and there's a 1/2 chance. So Q1 is 1/2. Well, what is Q2? Q2, well, you could consider casework, but you don't have to. Just plug in n equals to 2, and over here you have Q0, and here you have Q1. And we have a recursive relation to let us continuously derive Q3, Q4, Q5. We don't even need to do the probability ourselves, right? So this is what makes recursions so powerful. In combinatorial problems, recursions often allow you to basically focus on a certain case just based off the last move or the last 2 moves. And from that, you're able to build an algebraic relation, which allows you to basically start from some easy value and compute all the way to like Q10. Now in this case, notice that for P10, we need Q7. That's not so hard by this recursive formula, right? Okay, so here are our recursive formulas. Recall that we just wanted P10. So we know that we have a recursive formula for Qn, and Q0 is 0 and Q1 is 1/2. So we can get Q2 no problem. By this recursion, we have Q2 is 1/2 times Q1, which is 1/2, plus 1/4 times Q0, which is 0, right? Just plug in n to be 2. Okay, so this would actually evaluate to 1/4. Great. Now we can continue with this. What is Q3? Well, by this recursion, again, we have 1/2 times Q2, that's 1/4, plus 1/4 times Q1, that's 1/2. And this would actually evaluate to 1/4. Now, I'm not going to show you the details because I'm sure you know how to work with these fractions. So I'm just going to skip to the moment where I get Q7. It's just 13/128. And you can see the calculations don't take that long. So now that we know what Q7 is, we can get P10 no problem. P10, by the recursion over here, is equal to 1/4 times Q7. And this would be 1/4 times 13/128. That's it. So you can actually evaluate this to be 13. I'll write this equal sign a little bit better. This is equal to 13/512. And that's the answer. This is the probability that we are looking for. Now, I've said this in previous videos, and I'll say it again here. While the answer itself might be satisfying, the most important part is the problem-solving technique. In this case, recursions. Always remember that the purpose of recursions is to analyze the entire thing just based off the previous step or the previous 2 steps, or maybe even the previous 3 steps. The point is that you don't want to focus on the entire thing because that can be kind of complicated. In this case, a path of length 10. It was not very easy to focus on the entire path, but once we started analyzing it based off the previous step, we were able to derive a recursive formula. Basically, it told us how the probabilities are related algebraically. And we were able to start from some small value and build our way up to higher values. So whenever you find an opportunity to analyze an entire thing just based off the previous thing, consider recursions. It can save you a lot of time in combinatorial problems. Anyway, thank you very much for watching this video. If you found it helpful, if you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.